sir. Thank you, sir.
Then this boundary value problem can be expressed as f of t is equal to b minus a into t plus ab minus ba over b minus a plus integral from a to b g of t s f of s. This is just f of s. Where g is Green's function g of t s is minus 1 over b minus a into t minus a into b minus s for a less or equal to t is less or equal to s is less or equal to b. Also, g of t s is minus 1 over b minus a into s minus a into b minus t for a is less or equal to s is less or equal to t is less or equal to b. For this second order linear boundary value problem can be expressed in this way, where g of t s is Green's function defined here. Let's see proof of this theorem. This is consider given differential equation. This is d to f over dt square is f of t, where t belongs to ab. Just integrate this from a to t. So just integrate this. So you can see this is second derivative when integrate. So this is just first derivative dx over dt, and limits integration from a to t is equal to integral of this is a to t f of s ds, where t belongs to ab. This is just integrating this from a to t, so you can see this is.
सर ये किया हुआ है सर 2.3 थ्योरम
सर इसके लास्ट से कर लो
सर इसका नेक्स्ट पार्ट
2.1 के लास्ट
ओके
ओके सर हो गया थैंक
सर 2.3 भी प्लीज
नेक्स्ट टर्म जो है वो 2.4 है
सर 2.3
now use limits of integration, so we use upper limit, so this is dx over dt of t minus dx over dt at a is equal to a to t f of s ds, t belongs to ab. Now just shift this to right side, so you can see dx over dt at t is dx over dt at a plus a to t f of s ds, where t belongs to ab. Now integrate this from a to t. So you can see when you integrate this is first derivative, so just integrate this, so this is just x, and limits of integration from a to t, and this is dx over dt at a, so this is just a constant. So integral from a to t of this is just t minus a into dx over dt, plus this is just integral from a to t, then integral from a to s, f of tau d tau, here is ds, where t belongs to ab. Now this can be expressed as, this is x at t is x of t minus x at a is x of a is, and this is t minus a dx over dt at a, plus this integral can be expressed as integral from a to t into t minus s f of f ds, where t belongs to ab. Now this is x of t, just shift this to right side, so this is x of t is x of a plus t minus a into dx over dt at a, plus from a to t, t minus s f by ds, where t belongs to ab. Now this is now using the given boundary condition, so you can see this is x of t is x at a is just a, plus t minus a into dx over dt at a, plus a to t integral from a to t into t minus s f by ds. Now just substitute t equal to b, so you can see this is x at b is a plus b minus a dx of dt at a, plus integral from a to b into b minus s f of x ds. Now from here you can see x at b is equal to a plus b minus a dx over dt at a, plus integral from a to b into b minus s f by ds. Now just shift this to left side, so this is b minus a is b minus a into dx over dt at a, plus integral from a to b into b minus s f by ds. So from here you can see just shift this to left side, so you can see this is b minus a minus integral from a to b into b minus s f plus ds is b minus a into dx over dt at a, so dx over dt is just divide this by b minus a, so you can see dx over dt at a is b minus a over b minus a minus 1 over b minus a integral from a to b into b minus s f plus ds. So x of t is a plus t minus a. Just use this. Just use dx over dt at a. Yeah. In this equation, just use dx of dt at a here, so you can see x of t is so x of t is t minus a into b minus a over b minus a minus t minus a over b minus a integral from a to b into b minus s f plus ds plus integral from a to t into t minus s f plus ds. Now just taking LCM of these, so you can see this can be expressed as b minus a into t plus ab minus ba over b minus a minus, and this can be expressed as this integral from a to b. So first write this integral from a to t. So this is minus t minus a or b minus a integral from a to t into b minus s f plus ds plus this as it is integral from a to t into t minus s f plus ds. This integral is from a to b, so this can be expressed as integral from a to t, then integral from t to b. So just write this as integral from a to t, then integral from t to b. So this is minus t minus a or b minus a, so from t to b into b minus s f plus ds. Now this is b minus a into t plus ab minus ba over b minus a minus, just take LCM of these two, so you can see this can be expressed as b minus t or b minus a into integral from a to t into f minus a f plus ds minus this as it is, this is t minus a or b minus a from t to b into b minus s f plus ds. So this is, so you can see,
आपने बनाई और बनी
so you can see this is b minus a into t plus ab minus ba over b minus a, and this can be expressed as this is just Green's function for the integral from a to b, g of t as f of s ds. So you can see, this boundary value problem can be asked as in this way, where g is Green's function
सर
defined
प्रीवियस
here.
पेज कीजिएगा एक दफा स्क्रीन शॉट लेना
क्या?
सर प्रीवियस पेज एक दफा ऊपर कीजिएगा स्क्रीन शॉट लेना
Okay.
सर ऊपर ऊपर वाला पेज सर लास्ट से सर इसका आंसर जो आता है लास्ट वाला जी सर ले लिया था
Okay. आपने नोट कर लिया?
एक सेकंड जी सर कर लिए
Okay. Well, see another theorem. This is assume that f from AB cross R to R is continuous and satisfies a uniform differential condition with respect to x on AB cross R with the differential constant k, that is f of tx minus f of ty absolute is less or equal to k multiplied by f minus y absolute for all tx ty belong to AB cross R. As is continuous and is satisfy uniform differential condition with respect to second argument. This is with respect to x. So this is uniform differential condition. This is f of tx minus f of ty absolute is less or equal to k into f minus y absolute for all tx ty belong to AB cross R. Okay, if b minus a is less than 2 into 2 square root over k square root, then this second order boundary value problem, this is d to x over dt square is f of tx, where t belongs to AB, x at a is a, x at b is b. So if b minus a is less than 2 into 2 square root over k, then this boundary value problem has a unique equation. So, well, see proof of this theorem. This is for x is a Monod space of continuous functions on AB with norm defined as this is x norm is maximum of x of t, uh, maximum is over a less or equal to t is less or equal to b. So x is a space of continuous functions of AB, and this is norm defined in x. For any element x belong to x, you can see x norm is maximum of x of t absolute, where a is less or equal to t is less or equal to b. So x is a solution of this boundary value problem if and only if x is a solution of this integral equation. You can see this can be expressed as this. So x is a solution of this boundary value problem if and only if x is a solution of this integral equation. This is x of t is b minus a into t plus ab minus ba over b minus a plus integral from a to b g of ts f of x x of s ds, where g of ts is Green's function defined as g of ts is minus 1 over b minus a into t minus a into b minus s for a less or equal to t less or equal to s is less or equal to b. Also g of ts is minus 1 over b minus a multiplied by s minus a into b minus t, where a is less or equal to s is less or t is less or equal to b. Well, define a map t from x to x by t of t of x of t is b minus a into t plus ab minus ba over b minus a plus integral from a to b g of ts f of x x of x ds for t belong to ab. So the boundary value problem has a unique solution if and only if the map T has a unique fixed point. Because you can see if T has a fixed point, if T has a fixed point, then you can see and this integral equation has a solution. And if this integral equation has a solution, then you can see the given boundary value problem has a solution. So we use contextual mapping theorem to show that T has a unique point in X. Consider F5 belong to X and consider Tx minus Ty. So you can see Tx minus Ty absolute is just substitute in place. Tx is b minus a into t plus ab minus c, or b minus a plus integral from a to b g of ts f of x x of ds minus ty, just replace y in place of x. So you can see just subtract these two. So you can see this is cancelled with this plus integral. So this is less or equal to integral from a to b g of ts f of s x of s minus f of s y of s absolute ds. Just subtracting these two, so you can see this is. Now you can see f satisfy uniform mixture condition of f of s x of s minus f of s y of s absolute is less or equal to k into f of s minus y of s absolute, and this it is g of ts absolute. Integral is from a to b. So this is. Now this is k integral from a to b g of ts ds, and this is f of s minus y of s absolute is less or equal to x minus y norm. So this is. Now you can see integral from a to b of g of ts absolute ds is integral from a to t g of ts absolute ds plus integral from t to b g of ts ds. Now using g of ts, so you can see this is 1 over b minus a integral from a to t s minus a into b minus c ds plus this is 1 over b minus a into t minus a into b minus s ds integral over t to b. So this is. And this is integral with respect to s, so you can see b minus t can be taken outside. So b minus t over b minus a integral from a to t of s minus a ds plus. Also this is integral over with respect to s, so you can see t minus a can be taken outside. So this is t minus a over t minus a integral from t to b into b minus s ds. So this is just integrate these, so you can see b minus t over b minus a integral of this is f minus a square over 2 limits integration from a to t minus t minus a or b minus a integral of this b minus s square over 2 limits integration from t to b. So this is just substitute upper limit. So you can see this is b minus t into t minus a square over 2 into b minus a minus lower limit you substitute. So this is just 0 plus t minus a into in place of as substitute upper limit, so you can see this is 0 minus substitute lower limit, so this is b minus t square over 2 into b minus a. So this is just taking t minus a into b minus t over 2 into b minus a, just take common, so you can see this is into t minus a plus b minus t, so this is just b minus a, so this is cancel with this, so this is t minus a into b minus t over 2. Now this has a maximum value at t equal to a plus b over 2. So just substitute t equal to a plus b over 2. So this is less or equal to a plus b over 2 minus a into b minus a plus b over 2 over 2. So this is just b minus a square over 8. So integral of g of t as absolute from a to b dx is less or equal to b minus a square over 8. Now using this over here, so you can see tx minus ty absolute is less or equal to k into b minus a square over 8 into s minus y norm for t belong to ab. Now this is just tf minus ty norm is less or equal to alpha multiplied by s minus y norm, where alpha is this value, so alpha is k into b minus a square over 8, and this is given less than 1. So you can see this is a contraction. So t is a contraction. So by contraction mapping theorem, you can see t has a unique fixed point. So integral equation has a unique solution. So you can say, and the given boundary value problem also has a unique solution.